get things started here with just an intro to partial differential equations. Okay, and we will just call those PDEs. So, just looking back at what we've done so far with the complex, we remember we got to this Cauchy-Riemann equations. Okay, and if we look at a region as opposed to simply a point, what we would have for that is the partial of f with respect to x of z was equal to minus I times partial of f with respect to y of z. So notice this is an equation. That involves a dependent function or dependent variable. Okay, so a dependent variable, and its partial derivatives. And that's what makes it a partial differential equation. Okay, so any equation where we're talking about some unknown function usually. So here, if I typically when we try to use these, we actually know what f is, but the idea could be, well, I need a function that satisfies this equation, and you go looking for that, and usually you get extra information to help you with that. But that's all a partial differential equation is. So it's an equation that involves a function and its partial derivatives. So for the next part of the course, okay, so for the next part of the course, we're going to examine some particularly popular, or useful, I guess, or they just come up a lot. There are a lot of the base formulations for lots and lots of problems, and we'll try to see why. So particularly popular PDEs. Okay, and so trying to put a dot there. Okay, we're going to look at things like u sub t. So t is time, and x is space. So t is time, and x is space. So we'll look at something like this. This is called the heat equation, and we'll see where it gets its name here in a little bit. So that's the heat equation. Then the second partial of u with respect to t equals the second partial of u with respect to x, or the So the second derivative with respect to time is equal to the second derivative with respect to space. This we call the wave equation. And now, actually, in the case of the heat equation, if we let u sub t equal 0, actually, in this particular case, we would have then uxx equals 0, which is not a partial differential equation. That would just be a ordinary differential equation because there's only one independent variable there. But we also might look at two space variables. And so we might have something like uxx plus uyy is equal to 0, for instance. And but the idea there is, again, if we go back here and look at the heat equation, and we say the first derivative with respect to time is equal to the second derivative with respect to space, then if we sort of let this process go on, you could imagine in some cases, if we're talking about heat transfer, that it would reach an equilibrium kind of thing where the heat in something doesn't change over time. It just stays constant. Well, so in that case, we would get that u sub t is equal to 0, and so u sub xx equals 0, or if we had more space variables, something like this. And so those are the main things we're going to look at. We're going to look at some other modeling aspects of it, but those are the base sort of equations. And we'll be more interested in the modeling process. So where do these things come from? Than any analytic solution process. So, a number of these, we do know how to solve them analytically. We may look at that just a little bit, but that's not really going to be the focus. We'll use technology to help us solve some of these and kind of look at behaviors from there. So that's our introduction. That's what a partial differential equation is, and basically the main types we're going to look at and at least kind of start with and then go from there. And again, we'll use a lot of technology for the solution and not worry so much about the analytic methods. You could do that when you take a whole course in partial differential equations someday.